Welcome everyone. Today we're going to have Stan Moore at Sandia National Labs presenting LAMMPS. So if you have any questions, please feel free to ask, unmute and ask, or you can also leave it in chat and I can ask Stan. All right, go ahead, Stan.
Okay, thanks. Okay, so like was mentioned, I'm Stan Moore. I'm one of the LAMMPS co-developers at Sandia National Labs in Albuquerque, New Mexico. I've been at Sandia for about 10 years. I'm the main developer of the Cocos package in LAMMPS. Cocos is a performance portability library, which allows LAMMPS to run on GPUs and multi-threading on CPUs. I also have expertise in long-range electrostatics, and I received a PhD in chemical engineering, but I've been working on molecular dynamics for a long time, so my dissertation was on developing a new method for predicting chemical potential. Okay, so here's just a really high-level overview of molecular dynamics. So classical molecular dynamics model atom behavior using Newton's laws of motion. So what classical means is that we're neglecting electrons, and we typically use an empirical expression for forces. So we first start out with atom positions, and then we can use this empirical expression to get the forces, and then we can time integrate to get velocities and new positions and step through time. Because we use a spherical cutoff, we have linear scaling, which is proportional to the number of atoms, and so we can simulate billions of atoms on a supercomputer. And here's just a really simple example of molecular dynamics. You can see that we have atoms model as point spheres, and they bounce around through time. Okay, so we talked about molecular dynamics. So what is LAMMPS? LAMMPS is a open source C++ molecular dynamics code, originally developed at Sandia, but is has a large user base. We received code contributions from many people around the world. We can study biomaterials in mesoscale. Mesoscale is kind of a larger length scale than the atom, and LAMMPS is very large and has a lot of different models. So beyond just the traditional molecular dynamics, you can actually model electrons. There's also some coarse-grained systems, and you can even couple up to continuum. We use domain decomposition for parallelism. LAMMPS supports minimization, dynamics, as well as non-equilibrium molecular dynamics. We have support for accelerators, and LAMMPS can also be coupled to other length scales such as quantum mechanics, kinetic Monte Carlo, finite element, and computational fluid dynamics. Okay, so I just have a few slides. I won't get into too many details of the underlying physics, but I think a little background in statistical mechanics would help. So statistical mechanics is trying to relate basically the macroscopic observations such as temperature and pressure to the behavior of atoms. And the way that we can do this is looking at phase space and ensembles. So a phase space is basically the all possible states of a system. So if you have n particles, then that gives us 6 n-dimensional phase space because you have 3 position variables and 3 momentum. And if you take all of the atoms that can basically idealize that into a large number of virtual copies of the system, that's an ensemble. So if you consider those all at once, each of these represents a possible state of the real system. And so here's an example of different statistical ensembles. The most commonly used are NVE. So you can see here that it's constant number of atoms volume and energy. So it's like a adiabatic insulation here. You can also control the temperature or the pressure, represented here by a piston. Okay, so let's dive just a little bit deeper into molecular dynamics and look at a few equations. Nothing too deep, but the way that it works is you have initial positions and velocities. So you initialize your system. You could initialize it on a lattice or some other way. You set initial velocities, could be based on a temperature distribution, like, and then you have this interatomic potential. So typically an empirical representation, and then you use Newton's equations of motion, and then you can update to get positions and velocities at many later times. That allows the atoms to move around realistically. And if you look at the equations, like I said, there are 6 coupled ODEs, and then we use Newton's equations of motion to update the system. And as I said before, that we don't consider electron behavior. Okay, so what can you use molecular dynamics for? Well, a very classic application is material science. So you can look at metals, you can look at defects or cracks. You can also look at chemistry, so bonds breaking and forming. You can look at biophysics, such as proteins folding, granular flow, so like particles, like a packed bed or dust or some sort of granular flow, as well as coupling to solid mechanics. Okay, and let's talk a little bit about length and time scales. So the smallest length and time scales relevant are on the order of electrons. And so you can use quantum mechanical electronic structure calculations like DFT. These provide an accurate description of the atoms by modeling electrons. But because this is very computationally expensive and it scales, doesn't scale well with number of atoms, you're really limited to small system sizes, such as 1,000 atoms. And in order to look at interesting phenomena, you really need a larger scale. And so here's quantum mechanics, and then, this is on the order of angstroms, and then you have continuum or mesoscale models, which are on the order of millimeters to meters. And then time scales, you're looking at like 10 to the 15 all the way up to, microseconds or even milliseconds. And so really what we use large scale molecular dynamics is to bridge the gap between quantum mechanics and continuum. So as I said before, you can simulate on the order of 1 billion atoms on a supercomputer. Okay, so how do we actually model atoms in molecular dynamics? Well, here are some basics. So often the atoms are modeled as points, like finite size spheres. You can also use other shapes such as ellipsoids. You can model all the atoms, or you could do a coarse grain model, or even a meso or continuum scale model, like paradynamics with MD. You typically use like an orthogonal box, but it can also be skewed, and very commonly use periodic boundary conditions. So that's when an atom goes out one side, it comes in on the other. This can simulate a bulk fluid, and it reduces the finite size effect from boundary conditions. Okay, so here's a really simple example so these atoms here are attractive, these blue and green are not. You pull the system apart and you form a crack. So this is just kind of a really simple 2D toy model. Okay, so how do we get this empirical potential to relate atom positions to forces? Well, like I said before, the quantum chemistry solves the Schrödinger equation, which are electron interactions to get forces on atoms. So this is very accurate, but very expensive. And so, like I said before, it can really only simulate on the order of 1,000 atoms. So in molecular dynamics, we're using an empirical force field. Sometimes it may be fit to quantum data. It's not as accurate, but it is much, much faster. And so another trick that we use in molecular dynamics is to only consider pairwise or three-body or a few body interactions. And this allows linear scaling up to, say, 1 billion atoms. And here is a very simple interatomic potential. It's called the Leonard-Jones potential. And this is the energy versus pairwise distance. So that you can see if the molecules get too close, then they bump into each other in a repulsive wall. But far away, they have an attractive tail, which gives you, like surface tension or liquid vapor equilibria. Okay, so there are many, many different potentials, basically models of how to model atoms. Some are more expensive, some are less expensive, and typically the later potentials via year published are more expensive. So you have EAM and Sillinger-Weber are some mini body potentials, same with Tursoff. REACS is a reactive force field, and then GAP, SNAP are machine learning potentials that we'll talk a little bit about in the next few slides. Okay, so we talked about Leonard-Jones. It's just a really simple equation. Kind of on the other end of the spectrum, there's the REACS F of potential, the reactive force field. It can capture bond breaking information via a bond order parameter, but it's extremely complex. So you can see these are all the terms in the force field, and then each of these terms has many, many equations to model the physics. This is the bond order parameter. REACS also includes a charge equilibrium model. So charges can move around on the atoms. And so this is really just trying to code up all of the chemistry, explicitly into equations. On the other side, the state-of-the-art machine learning potentials kind of do the opposite. So we're trying, instead of trying to hard code in the physics, we train the so that they kind of automatically pick up the physics. So these machine learning potentials have 3 parts. We have a descriptor of the local environment. So we're trying to fingerprint kind of the neighbors and the environment that the atom is in. And then we can express energy and force as a function of these descriptors. And then we use a large amount of training data, which could be from ab initio calculations such as DFT. We use all of that training data to train the model. And so using these machine learning potentials, we don't have to understand all of the physics as much. We just need to generate a lot of good, accurate training data and then train our models. And so the SNAP machine learning potential in LAMMPS, we've done a lot of work over the past few years to improve performance on the GPU. And you can see that there's been over 30x speed up on a NVIDIA V100 GPU. And so this model is extremely optimized for NVIDIA GPUs. Okay, so we've talked about molecular dynamics, we've talked about force fields. Now, how do we actually interact atoms with each other? So the way that we do this for efficiency is to build a neighbor list. So as I said before, typically we'll only have pairwise interactions or maybe a 3-body interaction. And so we create a list of all the neighbors, and typically atoms will only interact with neighbors inside a spherical cutoff. So this is a 2D representation, but in 3D it would be a sphere. And so we build up a list of neighbors inside this sphere, and then we only compute interactions between neighbors in the list. We also include a skin distance. so that we don't have to build this neighbor list every time step. We can, kind of know the average displacement of atoms and size the skin accordingly. Okay, so with this neighbor list, when you have more than one processor, there's an option you can, there's an option because pairwise interactions, basically the force on one atom is the equal and opposite force on the other atom. And so if you have two interacting atoms on different processors, if Newton flag is off, then both processors compute their interaction, and the resulting force information is not communicated. If you turn this Newton flag option to on, then only one processor computes this interaction, and then you have to compute that to the other processor. And so basically turning Newton flag on saves computation, but increases communication. And whether or not that's faster depends on a lot of different things. It could be dependent on problem size, the length of the cutoff, if you're on a GPU or a CPU, how many processors you have, etc. But this is one option in LAMMPS that you can toggle on or off. And Newton off is typically better for GPUs because they have a lot of compute capability and communication is slow. Okay, so previously I showed a neighbor list with a full sphere, a full sphere interaction.
Yep.
But there's actually an option or a capability to only compute half the interactions, because like I said before, each interaction, so the force on one atom is the equal and opposite force on the other atom. And so you can do this basically in half, but this requires atomic operations if you're on, say, a GPU or using multi-threading. And the opposite is to compute the full interaction in the sphere, but this means that you're computing each interaction twice. So this atom would compute the interaction with this neighbor, and then when you loop over this atom, it would compute the interaction with this neighbor. So the computation is doubled, but it means that you don't have to communicate on the ghost atoms, which we'll talk about in a little bit. So the advantage here is that it does not require thread atomic operations for thread safety. So this is typically used on GPUs for the simple pairwise potentials. Okay, so let's talk about how we parallelize the computation in LAMMPS. So LAMMPS uses domain decomposition with MPI, message passing. And so here we have, again, a simple 2D diagram. So this is the domain or the subdomain of processor one. And so each processor owns a portion of the simulation domain and the atoms therein. But you have a complication of when an atom here has to interact. So say this, the cutoff is this large. This atom has to interact with this atom across processor domains. So how do we do that? Well, the way that we do it in LAMMPS is to use ghost atoms. So the processor domain is extended to include the needed ghost atoms based on the spherical interaction cutoff. And we copy the data of the atoms located on other processors. We also have to communicate when an atom migrates from one processor to another, but that only happens when the neighbor list is updated. So that's not as often as, we have to communicate the positions of the atoms. And then if we have our Newton flag on, we have to reverse communicate the forces back and sum those back onto the owned atoms. So again, if you have any questions or need clarification, please feel free to unmute and interrupt. Okay, so with this domain decomposition, we may have an inhomogeneity in our distribution of atoms, and that will lead to a load imbalance so that some processors have more work than others. And so the way that we get around this in LAMMPS is called load balancing. There can be both static and also dynamic options to load balance. So the most simple example, or the most simple option in LAMMPS of load balancing, is called the shift style. And this just shifts the planar cuts between processors. So here's the unbalanced case. You can see that the top left processors have many more atoms in their subdomain. Each box represents the subdomain of a processor. And then if we shift the cuts, you can see that it's much more balanced. It's not perfect, but we've made the subdomain smaller where there's more atoms and larger where there's less atoms. So this works really well for 1D density variations like a liquid gas interface, but it doesn't work as well for general 2D or 3D variations. And so we have another option in LAMMPS called RCB. And you can see in this movie here, this is a tiling method. It's very dynamic, and it's able to load balance much better this general 2D load imbalance where you have different numbers of atoms. It also works in 3D as well. Okay, so molecules have bonds, angles, and so the way that we represent this in LAMMPS is with different bond, angle, dihedral, and improper styles. So bonds are basically a constrained length between two atoms. So that would be like these two atoms. Angles are obviously constrained angle between three atoms. And then you also have a dihedral, which is an interaction between four atoms as well as an improper. And so LAMMPS can handle these different kinds of molecular topology using different styles and different models for these bonds and angles, etc. Okay, and just briefly, I want to talk about long-range electrostatics. So LAMMPS can simulate charge systems. So, if you had like a water molecule, you would have partial charges on the hydrogens and oxygens because of the dipole. And truncation, so the Coulombic interaction is a 1/r, and it's very long-ranged. And so just truncating it like we do with, say, a Leonard Jones, like that potential I showed you, with a spherical cutoff, is not a good solution because you are neglecting the long-range part. And it decays very slowly. And so the way we get around this is to use a Fourier space method or K-space to include the long-range part. So we have a particle mesh method, which is based on the Ewald sum. The P3M is usually fastest. It uses fast Fourier transforms to do the reciprocal space calculations. And so in LAMMPS, this would be the LAMMPS command. And the nice thing about the long-range electrostatics is you can actually vary the Coulomb cutoff. But if you include the K-space method, then you'll get the same answer. And so this is just a way to more accurately model point charges in LAMMPS. Okay, so we talked a lot about different aspects of molecular dynamics. And here is a representation of the basic molecular dynamics time step. So this is every time step, assuming you're not on a time step where you have to rebuild the neighbor list, which would be, say, every 5 or 10 or maybe even 20 time steps. So the first thing you do is you do an initial positions, or thus updating the positions and velocities. And then you have to do an MPI communication to update the ghost atoms so that you can do your parallel domain decomposition calculations. And then you're going to compute the forces. That could be the pairwise bonded that we talked about, and then the long range K-space. If you have Newton flag on, then you have to do another communication to take the forces on the ghost atoms and sum them back onto the owned atoms on the other processor. And then this is like a leapfrog velocity relay. So you do the final integrate, and then you can do output if you want to get some thermodynamic output, say the pressure or the temperature or the energies. You can also, LAMMPS is very modular, very flexible. It has a lot of diagnostics. So those could be scattered throughout the time step as well. Okay, so LAMMPS has several different files, and I just wanted to introduce you to the names, kind of the syntax of LAMMPS files. So the first type is the input file. So this is a text file with LAMMPS commands that are used to run a simulation. So this would be, setting the temperature, telling it how many time steps to run, what is the time step size, etc. After you run LAMMPS, you get a log file. This is a text file with thermodynamic output from the simulation. So, what was the energy, the pressure? You can customize this for your own simulation. If you want to get forces or other atom properties like velocities or charges, then you can use a LAMMPS dump file. So the dump file is a per atom property dumped out to a text file. If you want to do checkpoint restart in LAMMPS, then you use a restart file. This is a binary checkpoint file with the data, all the data needed to checkpoint and restart your simulation. And then there's also a data file. So this is a text file that can be used to start or restart the simulation. So if you want to set up the initial positions of a complex system, then you can use a data file. Okay, so we talked about electrodynamics, we talked about LAMMPS, a little bit about running. So how do you download LAMMPS? So there's a few different ways. LAMMPS is open source, it's on GitHub. You can go to GitHub LAMMPS, go to the releases, and then you can just clone the repo, or you could download a zip file. Doing a git clone is really beyond this tutorial. You'll have to look up some git tutorials. You can also go to the LAMMPS website, go to the download link, and also get a gzip tar file. So this will be, so you can download either a stable version or a development version. So the stable version, it's going to have a lot of rigorous testing, but it's going to be a little bit older. The development version is kind of the latest head of development. It's still tested, so we have regression tests that run on every single commit, every single pull request, but it's just not quite as rigorous as a stable version. It includes the latest features, the latest performance optimizations, the latest bug fixes, though sometimes we do backport bug fixes into the stable version. But it could have undiscovered new bug. So you're kind of on the bleeding edge with the development version. Okay, so how do you compile LAMMPS? So like I said before, LAMMPS, you can go to the documentation. You can look at instructions on how to build. You do need a C++11 compatible compiler, but it could be either GNU, Intel, Clang, etc. You need an MPI library, or if you want to run in serial, then LAMMPS has a built-in stubs library, which is basically sort of a dummy library for MPI that you can use, but then you won't get in any, you can only run on a single processor, a single MPI rank. And then there are two ways to build LAMMPS. You can either use the make files in source make, or you can use CMake. Both are supported, both are kind of equal pain to compile LAMMPS. So just, pick whichever one you are more comfortable with. Okay, so how do you run LAMMPS after you built it? Well, like I said before, there's documentation that you can look at. but the basic syntax is the executable and then -n for input, and then the name of the input script. So in serial, if you built this, this would be your binary LAMMPS executable. You would execute that -n, and then in.lj is just a standard Leonard-Jones benchmark. In parallel, you would do MPI run, specify the number of processors, and then the same LAMMPS run command. There are many other command line options, and you can look at those in the documentation here. Okay, so LAMMPS, like I said before, it's a very large code. It's very modular, and there are several different optional packages. So if you build LAMMPS, typically you'll just get the default code, which is fairly small. If you need some other optional package, so say you want to run the SNAP machine learning potential, then you have to include this package when before you build or during the CMake configure. So the way you do this with the traditional makefile based system, the GNU Make, is just make yes mlsnap or make no mlsnap. And then with CMake, you just enable this package equals yes. So this is true of of Reacts. So there's a package for Reacts. There's a mini body package that has different mini body potentials, and you can see all the different packages here in the documentation. Okay, so there are a few special optional packages called Accelerator Packages. So how do you run on GPUs with LAMMPS, or how do you run multi-threaded with LAMMPS? Well, you really need special code. So to run on NVIDIA GPUs, you need CUDA. To do multi-threading, you need Openmp. And so the way that you enable these special packages in LAMMPS is using an accelerator package. So there are 5 accelerator packages in LAMMPS: Openmp, Intel, Opt, GPU, and Cocos. And I will go through all 5 of these in the next few slides and explain what they are, the advantages, and how to use them. Okay, so the Opt package. So the Opt package is just basically, it's a pretty small, it just has a handful of optimized styles that run a little bit faster. They might vectorize better. This is a CPU package, so it doesn't run on the GPU. It's just, they're just a little bit faster than the default version of LAMMPS. And so first you have to compile LAMMPS with the Opt package. So like I said before, you have to make yes opt or package opt equals yes. And then you have to run using the suffix command. So you run LAMMPS just like normal. You have the same input script, so you don't make any changes to your input script. You just put one command line option, this -sf opt, and that's the suffix command. So what this does is it automatically appends this /opt suffix onto any style in LAMMPS that it can. So for example, if you're using the Leonard-Jones potential, LJ cut, then it will automatically append this to LJ cut opt. So as I said before, you don't have to make any changes to your input file. You just put this one command line option. And the suffix command is documented here in LAMMPS. Okay, so the Openmp package. So this allows Openmp multi-threading on CPUs. But one caveat I'll mention is that typically the MPI domain decomposition in LAMMPS is almost always faster than using Openmp on CPUs. So, you have the choice, say you have 4 processors, you could either run 4 MPI ranks or you could run 4 Openmp threads. For LAMMPS, it's almost always going to be faster to run 4 MPI ranks and not run 4 Openmp threads. The exception is that you're running MPI across many nodes. Sometimes you'll have high communication overhead for MPI. And so you can you can lessen that bottleneck by using some Openmp threads, and so that could be faster. So if you, the more nodes you have, the more cores per node, the larger the bottleneck could be. You know, the more you're strong scaling, the less work per atom, the larger the benefit for OpenMPI plus OpenMP. Another advantage is that the Openmp package may vectorize SIMD vectorization better than just the regular non-accelerated code. Okay, so again, you have to compile LAMMPS with this Openmp package first, and then you can run with more than one Openmp thread. So you set that using environment variables, and then you can just append the suffix, and you'll get the accelerated version of LAMMPS. Okay, so very similar to the Openmp packages, the Intel package. The main difference with the Intel package is that it allows the code to vectorize very well on Intel CPUs and even non-Intel CPUs, with or without Openmp threading. You can even use the Intel package in conjunction with the Openmp package. So if you're running on an Intel CPU or even any CPU, then this accelerator package is probably the fastest. But the caveat is that not all of LAMMPS has been ported to the Intel package. And so you have to check whether or not your styles are in this package. If they're not, then you won't get any speed up, because it will just run the normal non-accelerated version of LAMMPS. Another advantage of the Intel package is that it supports reduced precision. So you can do either a mixed FP64 and FP32, or a pure single precision FP32. And then similarly, you have to compile LAMMPS with the Intel package, and then you set this suffix style, but then you also need to set a few Intel package options. So this -PK Intel 0 OMP2 mode double, these are package options that are documented here. This is saying I'm going to use 2 Openmp threads and double precision for my calculations. Okay, so we talked about CPUs. Now let's talk about GPUs. So there are 2 accelerator packages for GPUs in LAMMPS. The first is called the GPU package. And there's a few differences between, so the second is the Cocos package, and we'll talk about the differences between the GPU package and the Cocos package. So the GPU package is really designed for one or more GPUs coupled to many CPU cores. So only a handful of parts of LAMMPS actually run on the GPU with the GPU package. The rest are running on the CPU. So for example, only the pair style, so the force computation, will run on the GPU. Your time integrator and any diagnostics will be running on the CPU. That's why you need typically more than one CPU core to parallelize the host computation. You also have to move atom-based coordinates like the positions and the forces back and forth between the CPU and the GPU every time step, because you do the force computation on the GPU, but then you have to bring that down to the CPU and update the positions with your time integrator, and then those positions get pushed back up to the GPU. You can do some overlapping if you have the K-space enabled. It provides NVIDIA, AMD, and even more general OpenCL support, and it also supports reduced precision, just like the Intel package. Okay, so running the GPU package is a little bit more complex. First, you have to compile the GPU library that's found in the libgpu folder in LAMMPS. So that's a separate compilation. And then you have to compile LAMMPS with the GPU package enabled. And then to run, it's very similar. You have this -SF GPU and then a package option. So this basically just says use the GPU package, and then I have 4 GPUs that I'm going to run on. And if you're on an NVIDIA GPU, it's best to use the CUDA MPS multiprocess service if you're using multiple ranks per GPU. This reduces some of the overhead of synchronization if you have multiple ranks that are giving work to the GPU. And it will automatically overlap if you have K-space. Okay, so that was the GPU package. Now let's talk about Cocos. So in general, Cocos is used by many different codes. It's not just LAMMPS. It's actually its own separate library, third-party library. And Cocos is an abstraction layer between the programmer and next generation platforms. So it allows the same C++ code to run on different hardware. So the goal of Cocos is basically write your code once, and then it will run on an NVIDIA GPU, it'll run on a AMD GPU, it'll run on an Intel GPU, it'll run on a CPU with multi-threading using different backends. So it could be a CUDA backend, a HIT backend, a SYCL backend, an Openmp backend, etc. And the way that this works is that you take loops and you map those onto these different backend languages. And then the other part of Cocos are Cocos views, which are basically data layouts that can be optimized for specific hardware at compile time. So you can change the layout of your Cocos view to either promote cache reuse on CPUs or coalescing on GPUs. Cocos is used on top of MPI, and if you want to see more about Cocos, then you can look at the Cocos GitHub wiki. Okay, so we've taken Cocos and we've implemented it into LAMMPS as the Cocos package. So how do you build and run Cocos in LAMMPS? Well, first of all, you have to use a C++14 compiler. The difference between Cocos and the GPU package is that the Cocos package is designed so that everything runs on the GPU, and you try to minimize the data transfer from GPU to CPU. So you're running your time integrator, you're running your diagnostics as much as possible, everything on the GPU, almost nothing on the CPU. The caveat is if you have some style that isn't ported to Cocos, then you'll have to transfer data down to the host CPU, do that computation, and then transfer data back up to the GPU, and that can give a slowdown. Cocos only supports double precision, FP64, and there are several package options that can toggle, a full neighbor list versus a half neighbor list that we talked about, Newton on versus off here. These are all documented here in the LAMMPS documentation. Okay, so how to use Cocos. So with Cocos, you have to install the Cocos package, as we talked about before. There's no third-party library that you have to build separately. It just gets compiled in automatically. You run like before. You set the suffix command -sfkk, and then you also have to add this -k on and then G4. So this -k on just says turn on Cocos and then use 4 GPUs. This could be T4 for 4 threads, like here. And all this is documented in the LAMMPS documentation. Okay, so that's a summary of the 5 accelerator packages in LAMMPS. There's a few other considerations that you need to keep in mind to get good performance when using multiple MPI ranks and multiple threads or GPUs. The first is your processor affinity. So you need to control how MPI tasks are assigned to nodes and cores. You can use that, for example, like the bind to core or different options in your MPI run command. You also need to pay attention to the Openmp variables if you're using multi-threading, such as OMP proc bind and OMP places. And then you also need to pay attention to NUMA bindings For example, if you're running a dual socket system, then you don't want the MPI tasks driving the GPUs on different sockets as the GPU. You want to be on the same socket. So these are different considerations you need to think about of how you are binding your tasks and your threads to the different resources that you have on your node. Okay, so how do you get started with LAMMPS? Well, a really simple benchmark is the Leonard-Jones benchmark. It's in the LAMMPS distribution under bench in.lj. It's just a very simple pairwise model. It's similar to an argon, liquid, or gas. You can see it's just basically a bunch of particles in a box, and they just move around like a gas would. So it's super simple, and that's where I would if you just want to start running LAMMPS, this is what I would use. And so how do you know if you're getting good performance? Well, LAMMPS will output a loop time at the end of a run. So this is an excerpt from a LAMMPS log file or the screen output. And at the bottom of your run, it will have a loop time. So this is the time in seconds it took, the number of processors, like the number of MPI tasks, the number of steps, and the number of atoms. And with this information, you can calculate the performance of the simulation. So how many time steps per second did you get? You also get a timing breakdown of different categories. So this is the pairwise force computation, the neighborless build, the MPI communication, the output, different diagnostics or the time integrator. This is a run for the Leonard-Jones benchmark. So this benchmark that I mentioned previously. And you can see that. So this might have been on a GPU. So it said the COM time is really high. So one caveat on a GPU is that this timing breakdown won't be accurate unless you set the CUDA launch blocking equals 1, which forces, so this basically prevents any overlap of kernels. You don't want to do this when you are running an actual simulation performance because it could slow down the simulation. But if you want to get an accurate timing breakdown, then you need to set this environment variable. Okay, so let's look at some performance of different potentials. These are all single node or single GPU. So we've talked about the Leonard-Jones potential. This is just a really simple pairwise potential. The embedded atom model or EAM is a mini body potential. And then this REACS FF is a really complex reactive potential. And then the SNAP machine learning potential is a very computationally expensive potential. So on the left, this is performance in millions of atom steps per second. So how many atoms times how many time steps in a second can you run? And then you're looking at increasing atom count. So like I said before, this is a full either Intel CPU Skylake node, so 36 cores, or a single V100 GPU. And you can see that for all the potentials on the GPU, you need enough atoms to saturate the threads. So for the cheap potentials like Leonard-Jones, you need something like about 1 million atoms to saturate the threads. If you go too large, then you run out of memory. So here there's no data point because you ran out of memory. And then you also start to fall out of the cache. So same for EAM. REACS, it's more memory intensive, so you run out of memory at a much sooner atom count or smaller atom count. For the CPU, it's the same. You need enough work to saturate the full node, but then you're relatively flat performance. You've saturated the CPU. If you look at the relative performance, you get up to about 400 for Leonard-Jones, not quite 200 for EAM, and then REACS is much more expensive at 2, and the same as SNAP. Like I said before, we've done a lot of work to optimize Snap for GPUs, and you can see that the gap between the CPU and the GPU is much higher, much larger for Snap. You get a much higher relative performance for Snap on the GPU versus the CPU. You know, with the Leonard-Jones potential, that's not the case as much. So this is just kind of to give you a general feeling of performance. Another aspect about Snap is that it exposes a lot more parallelism. It's very expensive. And because it exposes more parallelism, you can use a lot fewer atoms. So, you know, you're saturated around 8,000 atoms. But, you know, 8,000 atoms for Leonard-Jones, you're not even close to saturating the GPU. Okay, so I just wanted to talk a little bit about MD parallel performance. So in general, molecular dynamics parallelizes very well. The different parts of the time step can be done in parallel through domain decomposition. Typically, you'll just loop over atoms. And if you're strong scaling to a few hundred atoms per processor, then you can have a high communication overhead. There's not enough work. So, you know, you see that here. There's a high communication overhead, or there's just not enough work. Okay, so a few terms. Strong scaling. So this is holding the system size fixed while increasing the number of processors. Weak scaling is increasing the system size proportional to the number of processors. So if you have perfect strong scaling, then if you double the processor count, it will cut the simulation time in half. If you have perfect weak scaling, because you're increasing the size of the simulation proportional to the increase in number of processors, the simulation time will stay exactly the same, even though you made it larger. So in general, it's harder to maintain good parallel efficiency with strong scaling because the actual work decreases relative to the communication overhead. Okay, so in LAMMPS, you know, how do you visualize the simulation? So there's a few different options. There's actually a built-in LAMMPS dump command. So that's so the movies that I've showed in this style have all been created with the in situ LAMMPS dump command that's documented here. But there's also a few other options. There's the Visual Molecular Dynamics, or VMD program. So that's you know, you can download this program. It has a GUI. It runs on a Mac or different OS like Windows. And so this is like a nice GUI. And there's also Ovito, which also is a GUI. And so this image here of a pore collapse, this is created by Ovito. You can render very high quality images. The LAMMPS dump image, that is just something that you would add to your input script. And then LAMMPS would render that automatically as the simulation runs. And you can output multiple snapshots and create a movie. You can also dump out the atom positions and visualize that in VMD or OMD to create a movie as well. Okay, so finally, how do you get help with LAMMPS? You know, you have a question, or your simulation is crashing, or you just can't compile, or whatever problem. How do you get help? Well, the very first thing you should do is look at the LAMMPS documentation. LAMMPS has a very extensive, very good documentation here at docs.lamps.org. So first search there. But we also have a MatSci forum. So that there are archives. So, you know, LAMMPS has been around for a long time. And so there have been a lot of different questions asked, and the answers to those questions have been archived. And so you can search MatSci, or even just Google, or you can also join the forum and then post new questions. And, you know, hopefully get an answer to the problem that you're seeking. And then there's also a LAMMPS reference paper. So this is a journal article that gives an overview of the code, talks about the parallel algorithms, performance and highlights of its, the different capabilities. So this is a really good read just to give you an overview of LAMMPS, what it is, how it works. It has some performance on CPUs and GPUs, etc. So here's the DOI here. You can link to that. And then, you can also ask questions on the discourse channel for SC22, and I'll be checking for questions about LAMMPS and can respond there as well. So that's all I have. I thank you for your time, and I'll answer any questions.
Hello.
Hi.
I have some questions about the GPU package. So are there any limitations on the GPU package? Because I have run some example programs on the LAMMPS, and I discovered that in some situation, using the GPU package will fail to execute. So I don't have some solution about this. So for example, let me see, if the test case will use the Sphere package, then if I utilize the GPU Accelerator package, the LAMMPS will fail to run. So are there any solutions about this?
So I'm not sure about the Sphere package, but for all of these accelerator packages, only a portion of LAMMPS has been ported. And so the first thing to do would just be to check and see, are the styles, like the pair style, the fixes, etc., are those ported to the GPU package? Otherwise, it's probably not worth it to run the accelerator package, because you're just going to fall back to the vanilla code anyway, and there could be overheads. So that's the first thing. I don't think there's any acceleration of the Sphere package. I'm not sure though. I'd have to check. And then, this would be a perfect question for the MatSci form, or you can also, if you're sure that it's a bug, then you can submit a ticket on GitHub, like in the issue tracker. If you have a reproducer, then we could, run that and debug it. But yeah, I don't know the specifics of the GPU package with the Sphere. I'd have to go look. But like I said, if you have a reproducer that you could give us, like an input script and the data file, then we can definitely look at that.
Okay, I got it. So the conclusion is that the GPU Accelerator package doesn't support all the package, right?
Yeah, so you have to look and see, is your style supported? And the GPU package, it's more forgiving than Cocos, I would say, because you're already running a lot of stuff on the CPU anyway. And so if your force style, so your pair style is supported by the GPU package, then you could get speed up if that's the major part of the computation, the percentage of runtime. Then you could definitely get a speed up with the GPU package, and then just everything else will run on the CPU.
So, okay, I got it. Thank you very much.
Any other questions?
I have a question.
Sure.
Can you go back to the slide where you had the timing breakdown? So my question is about the CUDA option, CUDA launch blocking equals 1. So
Okay.
The timing breakdown won't be accurate without that option enabled. So you're saying that these timings are incorrect then? They will just be wrong results or wrong timings, and so you don't, that's the wrong result, right?
So this is only for the Cocos package. It doesn't apply to the GPU package. And yeah, so in the Cocos package, you can have some overlap between the different kernels, and there may not be a barrier for synchronization. And so the time will be misattributed to, there's no barrier in between the different kernels, and so the time will just all end up in COM when that's not the case. And so if you set CUDA launch block equals 1, then that will force it to have synchronization in between the different kernel calls, and you'll get an accurate timing breakdown. But you don't want to do that for performance. When you're measuring performance, this loop time will be accurate because it's the aggregate of all the times. So it's really just, if you have some big bottleneck, or if you turn on CUDA launch block equals 1 and you see 88% of your time is in COM, then that's a big red flag that could tell you, either you're not running enough atoms per processor, or you've done some suboptimal binding of your threads, like all of your tasks are on a single core, something's wrong.
Okay,
Did that
yeah.
answer your question?
Yes, it did. Thank you.
Other questions?
Okay, yeah, I think I don't see any questions either. So let's thank our speaker today. And yeah, if you have any more questions, I guess you can ask in discourse, SCC discourse. So yep, thanks, Stan.
Yep.
We can end the webinar here today then.